The most dangerous black hole known to science is not merely an object in space. It is a phenomenon so immense, so fundamentally destabilizing, that even the language of physics strains to capture what it represents. This cosmic engine bends light into spirals, rips stars into shreds of incandescent gas, and sculpts entire galaxies through forces invisible yet absolute. Its power is not confined to matter alone. It shapes time, stretches causality, and challenges the very concept of boundaries. When astronomers speak of black holes as monsters, it is not metaphor, but recognition of a reality that resists domestication by theory. Black holes are not all the same. Some remain relatively quiet, swallowing gas and dust in silence, while others flare like cosmic beacons, blasting out radiation more intense than the light of trillions of suns. What separates the merely dangerous from the truly catastrophic lies in a combination of mass, spin, and circumstance. A small stellar black hole hidden in the arms of a galaxy might feed slowly, unnoticed, like a predator lurking in shadow. A supermassive one, placed at the center of a dense cluster of stars and gas, becomes an apex force capable of altering the fate of entire star systems. It is easy to think of them as distant curiosities, irrelevant to life on Earth. Yet the psychological impact of their discovery has always reached far beyond astrophysics. The philosopher Blaise Pascal once wrote of his dread when contemplating the eternal silence of infinite spaces. That silence is no longer abstract. Black holes embody the silence with weight and consequence. They do not merely sit in the void, they create voids, erasing space itself. The terror lies not in their distance, but in what they reveal. That our universe is governed by laws that can erase form, identity, and history without hesitation. This recognition forces the human mind into altered states of perception. Consider how hypnosis bends awareness, focusing the subject on a narrow point of attention until the ordinary frameworks of thought dissolve. The pull of a black hole is similar, though infinitely stronger. Just as the hypnotic subject loses access to peripheral sensations, so light itself, under the influence of gravity this intense, loses the freedom to escape. Physicists describe the event horizon, a boundary from which no signal can return. Psychologists might recognize it as the ultimate cognitive blind spot, a zone where information falls away irretrievably. Danger, in the language of the psyche, is not only about destruction, but about distortion. When one looks at a black hole, one never sees it directly. Instead, one perceives its influence. The lensing of starlight, the warping of background galaxies into arcs and rings, the sudden flares of matter consumed at its edge. This indirectness carries an eerie similarity to illusions of the human mind. The Mueller-Lyer illusion, for example, convinces us that two equal lines are of different lengths simply because of the arrows that frame them. The black hole, too, presents illusions, arcs of light that are not really there, time slowed not in reality, but in perception. It is a theater of distortion, staged not by psychology, but by physics at its most uncompromising. And yet, this danger has an allure. The Event Horizon Telescope project, which linked radio observatories across Earth, captured in 2019 the first direct image of a black hole's shadow. The image of Messier 87's central black hole, a ring of fire encircling darkness, became an instant icon of scientific progress. But its effect was not merely technical. It resonated in art, culture, and consciousness. People described it as the eye of the void, a portal, a mirror to nothingness. These descriptions reveal something deeper, an encounter with knowledge that destabilizes certainty. Much like altered states induced by ritual chanting or sensory deprivation, Staring at that image invokes both awe and unease, as if looking into a truth beyond ordinary comprehension. What makes the most dangerous black holes so unsettling is not simply their scale, but their implications. They force a confrontation with mortality on a cosmic scale. Just as ancient myths of underworld gates warned mortals of passage points from which there was no return, the event horizon embodies that archetype in physics. Once crossed, no memory, no signal, no form survives. To study these objects is to stand at the edge of an abyss that science can describe mathematically, yet never fully tame. This is why their study has always carried an undertone of psychological consequence. The black hole is not only a threat to stars, but to meaning itself. To admit its reality is to acknowledge that the universe holds places where information ceases, where history is erased, and where existence itself unravels without trace. And still, humanity looks closer. Every measurement, every observation is a step deeper into the gravitational hypnosis of these objects. The pursuit is not idle curiosity. It is the recognition that danger is inseparable from knowledge, that the same forces which erase can also reveal. For in the darkness of black holes lies the potential to understand what no other phenomenon has ever exposed: the true structure of reality itself. The danger of a black hole is not a single quality, but the product of converging forces, each magnifying the others into extremes. Gravity is the most obvious. In Newton's vision, gravity was a force pulling objects together. In Einstein's general relativity, it became the curvature of space-time itself. A black hole is the point at which this curvature becomes so steep that escape is impossible. To describe such gravity is not to describe a pull, but a trap, one that reshapes the geometry through which matter and light move. The escape velocity at the event horizon exceeds the speed of light, not because the black hole exerts an ordinary force, but because space-time itself folds into an inward slope without exit. Yet, not all such slopes are equally menacing. The measure of a black hole's threat depends first on its mass. Mass determines the extent of its event horizon, the volume of space erased from causal communication with the rest of the universe. A stellar mass black hole might compress 10 times the mass of the Sun into a sphere only a few dozen kilometers wide. A supermassive black hole can concentrate billions of solar masses into a region wider than the solar system. The greater the mass, the larger the horizon, and the more catastrophic the consequences for any structure drawn near. Spin introduces another axis of danger. A black hole that rotates drags space-time in its wake, a process known as frame dragging. Matter approaching such an object does not simply fall inward. It is twisted around, accelerated into violent motion, and stripped of stability. The faster the rotation, the greater the distortion. In some cases, this rotation powers immense jets of energy that pierce intergalactic space, fueled by the interaction of magnetic fields with spinning plasma. The object does not simply consume, it projects, flinging high-energy particles across millions of light-years, transforming surrounding environments into fields of radiation. Environment provides the third determinant. A black hole isolated in a quiet region of space may remain invisible, its horizon cloaked in silence. Place the same black hole in a dense field of stars or within a cloud of gas, and its violence multiplies. Accretion disks form, rings of matter spiraling toward oblivion, heating to extraordinary temperatures through friction and collision. The light from such disks can rival that of an entire galaxy, creating a paradox. The darkest objects in the cosmos reveal themselves by becoming its brightest. The danger, then, is not solely in their hidden depths, but in the collateral destruction required to feed them. Even at safe distances, their influence is profound. Light passing near a black hole bends in arcs that betray the curvature of spacetime. Astronomers exploit this phenomenon to map distributions of matter, tracing the gravitational lensing of galaxies behind galaxies. Yet, for any object too close, lensing becomes a prelude to disintegration. Tidal forces stretch matter asymmetrically. One side of an object feels a stronger gravitational gradient than the other. This spaghettification, as it has been colloquially called, is not a metaphor, but a calculable process, reducing stars and planets into filaments of plasma. The psychological resonance of these processes is amplified by their invisibility. Humans are conditioned to fear predators with visible forms, claws, teeth, or shadowed silhouettes. A black hole presents none of these signals. Its presence is inferred only through what it destroys or distorts. Cognitive psychology suggests that ambiguity heightens anxiety. The mind fills absence with possibility, often more threatening than reality itself. The black hole embodies ambiguity perfected, a void given agency, an erasure that masquerades as a boundary. The concept of danger itself becomes unstable in this context. In daily life, danger implies a discrete threat, something that can be avoided, fought, or endured. But the danger posed by black holes cannot be localized. Their event horizons erase the distinction between interior and exterior, redefining what it means to occupy a place. Even time behaves differently in their proximity. To an external observer, a clock falling toward a horizon slows asymptotically, never appearing to cross. To the infalling clock itself, time proceeds normally until it terminates at singularity. This duality of frozen perception versus continuous experience introduces not only a physical paradox, but a cognitive one, an incompatibility of perspectives that undermines the very notion of shared reality. For neuroscientists studying altered states, the comparison is not distant. Under hypnosis or deep meditation, subjects often report time dilation or contraction, moments stretching or collapsing without clear transition. Psychedelic experiences have induced descriptions of timelessness, where seconds feel eternal or hours vanish in an instant. The brain's perception of time, reliant on oscillatory activity across cortical and subcortical networks, is malleable. In black holes, the malleability is not neural, but geometric. The parallel is unsettling. The cosmos mirrors distortions our own minds can fabricate, but with consequences no consciousness can negotiate. It is this combination: gravity without exit, spin without rest, environment without equilibrium, perception without stability. That defines the danger. Each element intensifies the others, producing an object whose threat cannot be captured by scale alone. A small black hole in a crowded stellar nursery may unleash chaos disproportionate to its size. A supermassive one in a sparse void may linger quietly, only to awaken if fed by a passing galaxy. Danger lies not only in what they are, but in what circumstances conspire to make them act. In the end, the universe offers no guarantee of distance or permanence. Black holes drift as galaxies merge, migrate, and collide. Their horizons are silent, but their reach is not fixed. To chart them is to recognize that the architecture of space is littered with wells of irretrievable descent, each one waiting for matter, energy, or light to fall. The boundaries of their menace are not neatly drawn. They expand and contract with circumstance, ensuring that their potential for devastation remains open-ended, contingent, and unresolved.
Black holes exist on a spectrum of scale, yet the extremes reveal profound differences in both origin and influence. At the lower bound are stellar black holes, the remnants of collapsed stars. When a star many times more massive than the Sun exhausts its nuclear fuel, gravity overtakes the pressure that once sustained it. The core implodes, crushing matter into densities beyond comprehension, while outer layers may explode outward in a supernova. What remains is a singularity wrapped within an event horizon a few dozen kilometers across, compact enough to vanish into invisibility, but powerful enough to consume everything that approaches. These stellar remnants are scattered throughout galaxies, often undetectable except through the light of companion stars or the high-energy X-rays produced by accretion disks. Stellar black holes are often measured in solar masses, typically ranging from 5 to perhaps a few dozen times the Sun's weight. Their destructive potential is immediate on a local scale. A binary system containing such an object becomes an arena of relentless exchange. Gas stripped from a star, accelerated by gravity, and heated to millions of degrees as it spirals inward. The emission of X-rays, captured by satellites such as Chandra or XMM Newton, exposes these invisible objects indirectly, much like shadows betray the existence of light sources. Such binaries have provided laboratories for studying matter at extremes of density, magnetism, and velocity. At the opposite end of the spectrum are supermassive black holes. These are not the relics of individual stars, but the architects of galactic centers. Their masses reach millions, even billions, of suns, compressing into horizons wider than planetary systems. The mechanisms of their formation remain contested. Some theories posit the direct collapse of massive gas clouds in the early universe, bypassing the stellar stage. Others suggest the gradual merging of smaller black holes over cosmic time, aided by dense stellar environments. Regardless of origin, their presence is near universal. Nearly every galaxy studied to sufficient depth reveals a supermassive black hole at its core, a gravitational anchor around which stars orbit as though bound to an unseen monarch. The difference between stellar and supermassive varieties extends beyond scale. In stellar systems, the gravitational field is lethal at close distances but diminishes rapidly with space. A planet orbiting a stellar black hole at safe remove may not experience anything unusual. By contrast, supermassive black holes exert influence on galactic architecture itself. Stars at vast distances move in orbits dictated by the central mass. Gas clouds collapse under its tug, fueling cycles of star formation and destruction. The black hole becomes a regulator of growth and collapse, a paradoxical engine of creation through the act of consumption. Intermediate black holes, with masses of hundreds to thousands of suns, are suspected but elusive. They may form in the dense cores of star clusters, where repeated collisions and mergers build gravitational wells larger than stellar remnants yet smaller than galactic giants. Evidence for such intermediates appears in faint X-ray flares or unusual stellar motions, but no definitive census exists. Their existence, if confirmed, would bridge a gap in the cosmic hierarchy and offer clues to how the largest black holes emerged so early in cosmic history. The psychological dimension of these categories lies in their disproportionate scales. Human cognition is poorly adapted to grasp orders of magnitude. Experiments in numerical cognition reveal that even educated minds struggle to intuitively distinguish between millions and billions. Stellar black holes, measurable in tens of kilometers, exist beside supermassive ones spanning billions of kilometers, yet both are described by the same equations. This dissonance mirrors illusions of scale encountered in perception. The moon appears large on the horizon yet smaller overhead, despite its constancy. The black hole spectrum confronts us with the same disorientation, identical principles applied across dimensions too vast for the brain to visualize coherently. Cultural traditions have often echoed this stratification of scale. In mythologies from Mesopotamia to Mesoamerica, underworlds were described as layered, with smaller gates leading to deeper, more formidable abysses. The stellar black hole resembles a local gate, immediate, dangerous, yet confined. The supermassive black hole echoes the archetype of a world-devouring void, a cosmic underworld seated at the axis of existence. Both forms mirror archetypal fears: the sudden collapse of the familiar and the inexorable pull of an ultimate center. The study of these scales has relied on increasingly refined instruments. Gravitational wave detectors such as LIGO and Virgo have confirmed collisions between stellar black holes, sending ripples across spacetime detectable billions of light-years away. These signals encode masses and spins, confirming predictions of relativity with precision. At larger scales, radio interferometry links observatories across continents to resolve the immediate environments of supermassive black holes, capturing the dynamics of plasma swirling at nearly the speed of light. Each category demands a different tool, a different lens, to reveal phenomena otherwise hidden behind horizons of silence. Yet the contrast between stellar and supermassive black holes is not merely observational. It carries consequences for survival. A stellar black hole passing through a star cluster may strip planets from orbits, igniting transient catastrophes. A supermassive black hole, once active, can unleash jets of radiation across millions of light-years, sterilizing regions of space from the possibility of life. Their dangers are not commensurate with their size alone. They unfold in contexts shaped by motion, density, and energy. What unites them is the principle of escalation. Small or large, silent or active, each black hole represents an unresolved potential. Stellar remnants may be born from single explosions, yet they hint at pathways to the giants that dominate galaxies. The giants, in turn, may awaken without warning, igniting ancient matter into flares visible across the universe. The spectrum of black holes is not fixed but fluid, a continuum of destruction and transformation waiting for circumstances to shift. Among the most extraordinary black holes known to science stands the one at the heart of Messier 87, a giant elliptical galaxy located some 55 million light-years away in the Virgo cluster. Designated M87*, it is not a relic of an individual star, but a colossus embodying billions of years of cosmic evolution. Its mass is estimated at about 6.5 billion times that of the Sun, concentrated into a region whose event horizon spans larger than the orbit of Neptune. To contemplate its scale is to engage with a gravitational field so commanding that it reshapes not only its immediate surroundings, but the structure of its host galaxy. M87* first came into broader cultural awareness in April 2019, when the Event Horizon Telescope collaboration released the inaugural image of its shadow. This shadow was not the black hole itself, which cannot be seen, but the luminous ring of superheated plasma encircling it. Radio observatories from across the globe have been synchronized into a single Earth-sized virtual telescope, applying the technique of very long baseline interferometry to resolve details impossible for a single instrument. The result was a blurred yet unmistakable vision, a circular glow surrounding a darkness that no light could escape. The sight carried both scientific significance and symbolic weight, becoming an icon of human ability to peer into regions of the universe previously thought unreachable. The power of M87* is most dramatically revealed in the relativistic jet it propels outward, a stream of particles accelerated to near the speed of light and extending more than 5,000 light-years into intergalactic space. Such jets arise from the complex interplay of gravity, magnetism, and rotation. Matter spiraling inward toward the black hole organizes into a disk, heated by collisions and sheared by tidal forces. Magnetic fields, twisted by rotation, funnel some of this plasma outward instead of inward, launching it as a coherent beam across cosmic distances. The scale of the jet in M87 dwarfs entire galaxies of modest size, a testimony to how an object defined by darkness can also become a source of blinding radiance. The destructive capacity of such a system is not limited to the immediate environment. Radiation from the jet floods interstellar and intergalactic space, influencing the formation of stars in the galaxy itself. Gas that might otherwise collapse into stellar nurseries is heated and dispersed, suppressing star birth. This regulation, known as feedback, makes M87* not merely a passive sink, but an active governor of galactic evolution. In this sense, the black hole embodies a paradox. It annihilates, yet through that annihilation it sculpts the trajectory of cosmic growth. Psychologically, the confrontation with M87* is a confrontation with excess. Human perception operates within ranges tuned to survival, distances in meters, weights in kilograms, durations in seconds. To engage with billions of solar masses and jets thousands of light-years long is to step outside the calibrations of the nervous system. Neuroscience studies of scale perception show that when numbers exceed certain thresholds, the brain no longer processes them as quantities, but as categories of large or small. M87* resides in that realm beyond number, where scale ceases to function as a measure and instead becomes a symbol of unbounded magnitude. In mythic traditions, excess often connoted the monstrous. The Greek titans were not simply large, they were embodiments of uncontrolled size, rivals to the gods. In Hindu cosmology, cycles of creation and destruction are guided by deities whose forms encompass countless worlds. M87* aligns with these archetypes, not as myth but as physical reality. Its jet, seen in optical and radio wavelengths, is a modern echo of fire-breathing dragons or divine lances that pierce the heavens. Science replaces myth with mechanism, but the psychological resonance persists. The study of M87* continues to expand. The Event Horizon Telescope's subsequent campaigns have aimed to refine the image, capturing changes in the ring's brightness over time. Such variability reveals the dynamics of matter at the threshold of collapse, where gravity, magnetism, and turbulence intersect. Models suggest that plasma near the event horizon may orbit at speeds approaching that of light, completing revolutions in days. To map these motions is to map the very fabric of spacetime under extreme curvature, probing relativity not as abstraction but as experiment. Yet the reach of M87* is not confined to astrophysical journals or scientific conferences. Its image has entered culture, invoked in art, literature, and philosophy as a symbol of absence and presence intertwined. The luminous ring suggests fire, life, and energy, while the central void embodies silence, erasure, and termination. This duality echoes deep structures of human cognition, where opposites define meaning. Light has no significance without darkness. Creation carries weight only in relation to destruction. M87*, by existing, becomes an emblem of this dialectic inscribed into the cosmos. For Earth, the threat from M87* is not immediate. Its distance ensures that neither jet nor gravity can touch our solar system. Yet distance does not diminish psychological impact. The recognition that such an object exists, and that countless others like it govern the centers of galaxies, reshapes our sense of security. We live in a universe where forces beyond comprehension are not rare anomalies, but structural components. The sky above, once navigated by constellations and myth, now conceals engines of erasure more powerful than anything imagination once conceived. What remains unresolved is how far human inquiry can penetrate into these domains. Each new observation sharpens understanding while deepening mystery. The plasma, the jets, the variability, the interactions with the host galaxy, all point toward processes that stretch the limits of both theory and technology. The confrontation with M87* is not a finished chapter, but an opening to further depths, a signal that behind the ring of fire lies a horizon science has only begun to approach. When black holes feed with unusual intensity, they reveal themselves not through silence, but through an eruption of radiance. These phases are known as quasars, objects so luminous that they can outshine the combined light of every star in their host galaxy. The word derives from quasi-stellar radio source, coined in the 1960s, when astronomers first identified mysterious points of light that resembled stars yet emitted energies impossible for ordinary stellar objects. What became clear through successive observations was that these were not stars at all but black holes in states of furious accretion, converting infalling matter into torrents of electromagnetic radiation. The mechanism is violent and paradoxical. As gas and dust spiral inward toward the event horizon, friction and compression heat them to extraordinary temperatures. Particles collide, releasing X-rays and gamma rays. Magnetic fields entwine with this motion, accelerating charged particles and funneling them into jets. The black hole itself remains invisible, but the environment surrounding it becomes one of the brightest phenomena in the universe. The efficiency of energy conversion in such systems surpasses that of nuclear fusion. A small amount of mass consumed by a quasar produces more radiation than millions of stars burning in unison. Quasars were among the first cosmological beacons to reveal the scale of the universe. Their redshifts, measured by Martin Schmidt in 1963, indicated that they lay billions of light-years away. To shine so brightly across such distances implied luminosities unparalleled in astrophysics. Some quasars emit thousands of times more energy than the Milky Way, yet all of it originates from a region no larger than the solar system. The juxtaposition of size and power underscores the extremity of the processes at play, where the collapse of matter into darkness paradoxically fuels the birth of light visible across cosmic epochs. The psychological effect of encountering quasars lies in their dissonance. They appear as stars in early images, simple points of light. Yet behind the point is a system so ferocious that its radiation shapes intergalactic space. Cognitive studies on pattern recognition reveal that humans tend to misinterpret points of light as familiar forms, a phenomenon exploited in navigation, storytelling, and mythology. For millennia, bright stars were guides and deities. In the telescope's field, quasars mimic this appearance, but their reality subverts expectation. They are not guides but warnings, not life-giving suns but furnaces of annihilation. The very act of misrecognition mirrors the illusions of perception documented in psychology, where the brain's drive for pattern leads to confident yet false interpretations. Beyond their deceptive simplicity, quasars have become indispensable tools for science. Because they shine across billions of light-years, their light traverses vast stretches of intergalactic medium before reaching Earth. Absorption lines imprinted on this light reveal the composition of intervening matter, mapping the distribution of hydrogen and heavier elements across the early universe. In this sense, quasars act as backlights illuminating the structure of the cosmos, their danger transforming into utility. Yet the fact that the universe's largest searchlights are born of processes so violent sustains the unsettling impression that illumination is inseparable from destruction. Not all black holes reach quasar phase. Conditions must align: a plentiful supply of gas, a gravitational environment conducive to accretion, and often the perturbation of galactic collisions. When galaxies merge, tidal forces drive gas toward their centers, feeding dormant black holes and igniting quasar activity. These periods can last millions of years, brief on cosmic scales yet long enough to alter the fate of galaxies. During such phases, radiation pressure can sweep gas out of the galactic nucleus, halting star formation and reshaping stellar populations. The balance between feeding and quenching, destruction and regulation, remains one of the central dynamics of galactic evolution. Human attempts to conceptualize quasars often drift into metaphor. They resemble torches lit in primordial darkness, but torches that consume rather than illuminate. Ancient mythologies spoke of fires that never extinguish: the Zoroastrian sacred flames, the Greek Promethean gift of fire stolen from the gods, the eternal pyres of Vedic rituals. Quasars echo this imagery but invert its meaning. They are eternal only on scales beyond human grasp, and their gift is not life but entropy. The cultural resonance of unquenchable fire is here reborn as a scientific reality, yet one stripped of benevolence. From a neurological perspective, The impact of contemplating such extremes may parallel altered states induced by meditation or trance. Brain imaging studies show that exposure to vast scales or overwhelming imagery activates networks associated with awe, particularly the medial prefrontal cortex and regions of the parietal lobe involved in self-representation. These states diminish the sense of individual importance, producing feelings of dissolution or smallness. Quasars, though remote, operate as stimuli of this kind. They are natural triggers of existential awe, inducing a psychological realignment where ordinary concerns collapse against the immensity of cosmic processes. Yet beneath this resonance lies a more immediate tension. The radiation of quasars, if directed toward inhabited systems, would sterilize them. Their jets, composed of relativistic particles, carve paths across intergalactic space like lances of energy. Simulations suggest that galaxies hosting quasars can become inhospitable across wide regions, their gas stripped or ionized. The same radiation that allows us to see them across billions of years could, in different circumstances, erase the possibility of observers altogether. The dual nature of quasars, as both guides and threats, lingers as a reminder that the universe's most informative beacons are also instruments of annihilation. This duality leaves the inquiry open-ended. Each new observation sharpens our picture of how matter behaves at the threshold of collapse, but it also underscores the precarious balance between growth and erasure written into the structure of galaxies. Quasars do not simply illuminate the past. They remind us that destruction on unimaginable scales is woven into the very fabric of cosmic history, waiting for conditions to converge once again. The destructive potential of black holes reaches its most vivid expression in the encounter with stars. When a star strays too close to a massive black hole, the event is neither a quiet swallowing nor a simple disappearance. It unfolds as a tidal disruption event, a process in which the gravitational gradient tears the star apart before it ever reaches the horizon. One hemisphere of the star feels a stronger pull than the other. The result is elongation, then fragmentation, until stellar matter is stretched into filaments of plasma spiraling toward accretion. What once burned as a coherent fusion furnace is unraveled into gas and dust, reassembled into luminous arcs around the black hole. Such events are rare on human timescales, but astronomers have begun to detect them across distant galaxies. They are identified by sudden flares of ultraviolet and X-ray radiation, followed by months or years of decline as the stellar debris gradually disappears into the central abyss. Unlike supernovae, which explode outward, tidal disruption events collapse inward, producing signatures distinct in both light curve and spectrum. Instruments like NASA's Swift Observatory and the European Space Agency's XMM Newton have documented multiple such occurrences, each one a record of a star's final moments translated into waves of radiation detectable across cosmic distances. The violence of tidal disruption illustrates the power differential between star and black hole. Stars represent stability, nuclear fusion balancing gravity for billions of years, producing the light that shapes ecosystems and civilizations. Black holes represent imbalance, gravity without counterforce, collapse without equilibrium. When they interact, the stability of the star yields instantly. In psychological terms, it mirrors the confrontation between ordered identity and overwhelming trauma. Just as the nervous system can be pushed into fragmentation by stresses too great for integration, a star cannot maintain coherence in the face of the gravitational asymmetry imposed by a black hole. The analogy is not poetic license but an illustration of how systems, biological or astrophysical, fracture when confronted by forces beyond their thresholds of resilience. The energy released during such destruction rivals or exceeds the brightness of entire galaxies. Some tidal disruptions eject matter at relativistic speeds, forming transient jets detectable in radio wavelengths. Others flood their host galaxies with radiation, briefly transforming quiet galactic centers into beacons visible from Earth. These outbursts are not mere footnotes in cosmic history, They contribute to the heating of interstellar media, altering the conditions for subsequent star formation. The erasure of one star becomes part of the scaffolding for future structures, destruction repurposed into creation by the cycles of galactic evolution. Beyond the destruction of ordinary stars lies the more unsettling scenario of black holes consuming neutron stars. Neutron stars themselves are already extreme, collapsed remnants with masses exceeding the Sun's, compressed into spheres no larger than a city, where matter exists as degenerate nuclear material. When such an object encounters a black hole, the violence surpasses imagination. Gravitational wave detectors have recorded mergers of this kind, their ripples propagating through space-time and detected across Earth. The signals encode the dynamics of the collision, the inspiral, the tidal distortion, and the eventual swallowing. In some cases, the merger also produces electromagnetic counterparts, flashes of light coinciding with the gravitational waves. The universe, in these moments, speaks through both geometry and radiation, testifying to the annihilation of objects already at the limits of physical endurance. The neurological resonance of these collisions emerges from the human inability to sustain coherent images of annihilation at such scales. Studies on cognitive overload show that when the brain encounters magnitudes beyond comprehension, it substitutes abstract categories for precise representations. Words like immense or infinite become placeholders where imagination falters. The black hole consuming a star operates precisely in this domain, a spectacle where the mechanics are calculable but the imagery resists visualization. The confrontation triggers not understanding but awe, a mixture of fascination and dread rooted in the brain's conflict between abstraction and sensation. These encounters also carry implications for planetary systems. A black hole need not consume a star directly to destabilize its satellites. Gravitational tides can disrupt orbital harmony, flinging planets into interstellar space or pulling them into lethal spirals. The vulnerability of planetary systems near galactic centers is heightened by this instability. Exoplanet surveys suggest that habitable zones are rarer in such regions, their prospects diminished by the proximity of black holes and the recurrent threat of stellar disruption. Life, as fragile equilibrium, depends not only on local conditions but on the distant architecture of gravitational giants. The observational pursuit of tidal disruption events has become one of the frontiers of astrophysics. The Vera Rubin Observatory, now nearing completion, promises to survey the entire night sky repeatedly, capturing transients with unprecedented frequency. Its data may reveal dozens or hundreds of stellar destructions per year, transforming rare spectacle into regular signal. Each detection will refine models of accretion, magnetism, and relativistic jet formation, building an atlas of catastrophe that extends across the observable universe. Yet each observation also sharpens the existential tension. The universe demonstrates that order can be undone in moments, that stability measured in billions of years can unravel when paths intersect with gravitational singularities. The lesson is not comfort but contingency. Stars, like systems of thought or memory, persist only while insulated from forces beyond their threshold. Once proximity breaches that insulation, fragmentation is inevitable. The cosmos, in this sense, mirrors the fragility of coherence in every domain where complexity exists. The horizon of inquiry remains open. For each flare detected, countless others occur beyond current sensitivity. The sky is filled with erasures too faint or distant to register, their signals lost in noise. To expand sensitivity is to uncover more records of destruction, more evidence that collapse is not anomaly but pattern. The prospect of detecting these hidden catastrophes draws research forward, ensuring that the narrative of black holes and stars remains unfinished, defined by the tension between what is seen and what still eludes observation. Black holes do not remain confined to the silent heart of galaxies. In some cases they move, driven from their place of origin by gravitational recoil or the chaotic interactions of galactic mergers. These are the so-called rogue black holes, objects cast adrift across interstellar space without a stable orbit or a fixed anchor. Their existence transforms the concept of danger. Instead of a stationary abyss awaiting approach, they become predators without territory, wandering through regions where stars and planets may lie unsuspecting. The mechanism behind such ejections is rooted in gravitational wave physics. When two black holes merge, the emission of gravitational radiation can be asymmetric, carrying momentum in one direction more than the other. Conservation of momentum dictates that the merged remnant recoils in the opposite direction, sometimes at velocities of thousands of kilometers per second. If this speed exceeds the escape velocity of the host galaxy, the black hole is flung outward, destined to roam intergalactic space. Even when the velocity is insufficient for escape, the black hole may oscillate through its galaxy, displaced from the center, altering the dynamics of stars around it. Evidence for rogue black holes is indirect but persuasive. Astronomers have identified quasars whose emission lines appear displaced, suggesting that the central black hole has been kicked away from its galactic nucleus. Hubble observations have also revealed arcs of disrupted stars trailing possible wanderers, consistent with simulations of ejected black holes carrying remnants of stellar systems with them. The invisibility of these objects complicates detection, but their gravitational influence betrays them in the same way shadows betray light, not by being seen directly, but by distorting what surrounds them. The psychological dimension of rogue black holes is sharpened by the erosion of boundaries. A stationary danger can be avoided with distance. A mobile one transforms safety into uncertainty. Cognitive studies on risk perception show that unpredictability amplifies fear. Threats without pattern are perceived as more severe than those with predictable intervals. The rogue black hole embodies this principle on cosmic scales. Its trajectory is not charted, its arrival not forecast. A planetary system may endure billions of years of quiet stability, only to find its orbits unraveled by a dark mass passing silently through. The possibility of rogue encounters also influences the search for life beyond Earth. Planets ejected into interstellar space are often theorized as cold and barren, but a passing black hole could destabilize their orbits long before ejection. Habitability is not simply a matter of local conditions. It depends on the larger gravitational landscape. In regions where mergers and recoils are more common, the probability of life achieving long-term continuity may diminish. The fragility of stability is exposed not by catastrophe alone, but by the threat of unannounced displacement. Rogue black holes also offer laboratories for testing fundamental physics. Their passage through gas clouds may generate shock fronts detectable in radio wavelengths. If they retain accretion disks, faint emissions of X-rays may trail them across the sky. Future instruments, such as space-based gravitational wave detectors, may be able to identify them directly by listening for the low-frequency ripples produced as they interact with stars. Each detection would carry implications not only for astrophysics, but for the narrative of cosmic order itself, revealing a universe in which its most destructive engines are not fixed but migratory. The cultural echo of such wandering entities can be traced across myth and folklore. Nomadic demons, restless spirits, and wandering giants recur in traditions worldwide. They represent forces without home, transgressors of boundaries, disturbers of order. Rogue black holes resonate with these archetypes not as metaphors, but as embodiments of restlessness inscribed into physical law. Their motion is not voluntary, yet it mirrors the symbolic restlessness of figures that resist confinement, moving endlessly across landscapes of myth and cosmos alike. The implications extend further when one considers the velocity scales involved. At thousands of kilometers per second, a rogue black hole could traverse an entire galaxy in a fraction of its lifetime. Its path may intersect molecular clouds, triggering new episodes of star formation while erasing others. In some scenarios, Simulations suggest that a rogue black hole could carry with it a retinue of bound stars, a miniature cluster traveling with the gravitational core intact. To encounter such a system would be to encounter a displaced galaxy seed, an object both destructive and generative, erasing orbits while seeding new arrangements in its wake. For human imagination, the rogue black hole represents a threat that eludes containment. Unlike supernovae, which erupt at known lifespans, or stationary galactic cores, which can be mapped, the Wanderer operates in opacity. The night sky may harbor such objects even now, their signatures too faint for current detection. They move without warning, their gravitational reach invisible until its effects are already unfolding. This uncertainty magnifies their presence, not as immediate danger but as unresolved possibility, an ongoing condition of exposure to forces unmeasured. Astronomers anticipate that the coming decades will sharpen the ability to track these wanderers. Advances in astrometry promise to detect the minute perturbations of stars displaced by unseen masses. Sensitive surveys may capture the brief flickers of accretion as rogue black holes graze through interstellar clouds. Yet even with detection, prediction remains elusive. Their trajectories cannot be forecast across billions of years without precise knowledge of every gravitational interaction. The unresolved tension persists. The universe contains moving abysses whose paths intersect with the fragile architectures of galaxies, and no calculation can erase the uncertainty of encounter. The destructive influence of black holes is not restricted to the stellar or galactic scale. It extends down to the level of individual bodies and the forces acting on them. The process most commonly invoked in describing such encounters is spaghettification, a term whose almost playful tone belies the severity of what it represents. The phenomenon arises from tidal forces, the difference in gravitational pull between one end of an object and the other. Near a black hole, this gradient becomes so extreme that it elongates any object into a narrow filament, stretching it lengthwise while compressing it laterally. 4 small black holes with masses only a few times greater than the Sun, spaghettification would occur well before the event horizon. A spacecraft or human body approaching such an object would feel the effect at considerable distance, the feet pulled far more strongly than the head, the structure of the body torn apart molecule by molecule. 4 supermassive black holes, paradoxically, the tidal gradient at the event horizon is weaker, since their radius is immense compared to their density. In such cases, an observer might cross the horizon without immediate spaghettification, experiencing the distortion only deeper inside. This divergence underscores how scale alters danger. Size does not merely increase power, but reshapes the geometry of its expression. The physics of tidal stretching reflects a more general principle of instability. When systems are exposed to differential forces exceeding their structural thresholds, they unravel. The human brain recognizes such processes intuitively. Psychological experiments on perception demonstrate that asymmetry attracts attention because it suggests imbalance or rupture. Spaghettification, though a technical term, resonates with this intuition. The object is no longer whole, no longer balanced, but drawn into disproportion until it ceases to exist as an identifiable entity. Observationally, spaghettification may leave traces in the form of flares produced as disrupted matter heats during infall. Recent detections of sudden brightening near galactic centers have been interpreted as stars or compact bodies being tidally shredded, their remnants producing bursts of light across multiple wavelengths. These detections are not merely dramatic spectacles. They provide rare opportunities to study the structure of black holes indirectly, using the shredded bodies as probes of regions otherwise inaccessible. The destruction of one object becomes the key to unveiling the invisible contours of another. The psychological dimension of spaghettification confronts human cognition with the prospect of dissolution into scale. Identity, memory, and continuity rely on coherence. When imagining a process that strips coherence away, the self is placed under a thought experiment of annihilation. Neuroscientific research on depersonalization experiences reveals that the mind resists such imagery, often substituting metaphor or abstraction in place of detail. To picture one's body elongated into a filament of atoms is to encounter the limits of visualization, a confrontation not only with mortality but with the unmaking of form itself. The broader astrophysical consequences of tidal forces extend beyond individuals. Stars, gas clouds, and even small galaxies can be disrupted by larger black holes. Dwarf galaxies approaching a massive host may find their stellar populations stripped, leaving behind streams of stars stretched across intergalactic space. These tidal tails, observed through wide-field surveys, map the gravitational influence of black holes and dark matter halos alike. What occurs on the scale of a human body near a stellar black hole repeats across magnitudes of scale, a fractal of disruption inscribed into the mechanics of gravity. The cultural echoes of stretching and dissolution appear in myths of transformation and fragmentation. Ancient stories of beings torn apart and remade, the Egyptian Osiris dismembered and reassembled, the Norse Ymir whose body formed the world, resonate with the imagery of matter pulled apart and redistributed. In the scientific narrative, spaghettification does not lead to renewal but to absorption, yet the symbolic parallel remains: destruction as a passage into another state, where parts lose individuality and merge into a larger whole. Technological imagination has also grappled with these forces. Theoretical designs for probes venturing near black holes confront the inevitability of tidal stress, requiring concepts of materials resistant beyond any known strength. The impossibility of such resilience highlights the limit of engineering when faced with gradients that no substance can withstand. Even speculative physics, invoking exotic matter or hypothetical shielding, cannot circumvent the underlying asymmetry of spacetime itself. The force is not external but structural, woven into the geometry through which everything must move. The study of tidal disruption continues to expand as instruments improve. High-energy observatories capture transient X-ray outbursts, while infrared telescopes track the cooling remnants of disrupted material. Each detection contributes to a growing catalogue of spaghettification events, transforming an abstract concept into an observable phenomenon. The accumulation of data does not diminish the strangeness but amplifies it, reminding us that processes which sound almost absurd in description are, in fact, routine occurrences across the universe. Yet the tension persists. For every star shredded and every flare detected, countless encounters unfold unseen, their signals lost in cosmic distance. The very nature of spaghettification ensures invisibility beyond a point. Once the debris crosses the horizon, no record escapes. What remains observable are only the fringes, the preliminary phases before erasure completes itself. Science can reconstruct the outlines of destruction, but never its culmination, leaving a space of unresolvable opacity at the core of the process. The narrative of tidal forces, stretching from the molecular to the galactic, remains unfinished. Each encounter leaves partial traces. Each observation raises questions about what lies beyond detection. The geometry of spacetime promises more secrets than current instruments can uncover, and the abyss into which filaments of matter vanish continues to expand as both a physical boundary and a conceptual horizon. The event horizon, often described as a boundary of no return, is not a tangible surface but a geometric threshold. It marks the radius where the escape velocity equals the speed of light, sealing off the interior from external communication. For decades, the event horizon was regarded as an absolute veil. Once crossed, all information was lost to the outside universe. Yet developments in theoretical physics have destabilized that certainty, suggesting that horizons may be more porous than once imagined, not in practice but in principle, with profound consequences for our understanding of reality. The problem arises from the interplay of quantum mechanics with general relativity. In the 1970s, Stephen Hawking demonstrated that black holes are not entirely black but emit radiation due to quantum fluctuations at the horizon. Virtual particle pairs continually form and annihilate in the vacuum. Near the event horizon, One particle may fall inward while the other escapes outward, producing what is now called Hawking radiation. Over immense timescales, this process leads to evaporation, gradually reducing the mass of the black hole. The implications are unsettling. If black holes evaporate, then the information contained within them seems destined to vanish as well. Quantum theory, however, maintains that information cannot be destroyed. This tension, known as the information paradox, has become one of the deepest puzzles in modern physics. It questions whether the laws of the universe preserve the coherence of history, or whether some records are erased without trace. The paradox is not an abstract concern. It touches the very structure of causality and the integrity of physical law. Attempts to resolve the paradox have produced a landscape of competing hypotheses. One proposal suggests that information is encoded in subtle correlations within Hawking radiation itself, though detecting such correlations would be extraordinarily difficult. Another argues that information remains imprinted on the event horizon in a kind of holographic form, accessible in principle even if not in practice. A third, more radical suggestion posits that black holes may terminate in violent releases of stored data as they evaporate, a theoretical firework that restores information at the final moment. Each possibility reshapes the conceptual boundary between destruction and persistence, between erasure and record. From a psychological perspective, the paradox resonates with anxieties about memory. Human identity is built upon continuity of recollection. Amnesia or erasure threatens coherence of self. When physics presents a scenario where the universe itself might forget, the analogy is immediate. Experiments on cognitive dissonance show that humans struggle when faced with contradictions between two trusted frameworks. The conflict between relativity, which suggests information loss, and quantum mechanics, which forbids it, mirrors the cognitive distress of holding incompatible truths. The paradox becomes not only a problem for physics, but a reflection of the limits of comprehension when fundamental laws collide. The holographic principle offers one of the most influential responses. Proposed by Gerard T. Hooft and elaborated by Leonard Susskind, it suggests that all the information contained within a volume of space can be described by data encoded on its boundary surface. Applied to black holes, this principle implies that everything falling in is somehow recorded on the horizon itself. The interior becomes redundant. Reality, at least mathematically, is a projection from the surface. If true, the universe may itself be holographic, with three-dimensional experience emerging from two-dimensional information structures. Such a perspective destabilizes common intuitions. The solidity of volume, the depth of space, the persistence of form, all may be derivative of encoded surfaces. In neuroscience, similar questions emerge regarding perception. The brain constructs three-dimensional representations from two-dimensional retinal input, synthesizing depth from flat data. The holographic principle echoes this neurological process at cosmic scale, suggesting that experience itself may be a reconstruction, not of matter directly but of encoded information. The paradox also raises questions about horizons themselves. If information is preserved on the surface, then crossing the horizon might not be the erasure once believed, but a translation into boundary code. This leads to speculative constructs such as black hole complementarity, where different observers experience reality differently yet consistently. The infalling traveler perceives uninterrupted passage into the interior, while the distant observer perceives the traveler's information smeared across the horizon. Both accounts are valid within their frames, though mutually irreconcilable. The multiplicity of truths recalls the psychological phenomenon of bistable perception, where the same image, such as the famous duck-rabbit figure, supports two incompatible interpretations without resolution. Experimental approaches to these questions remain indirect, but are advancing. Observatories tracking gravitational waves may capture subtleties in black hole mergers that hint at horizon properties. The Event Horizon Telescope continues to refine its images of shadows, probing whether edges align with relativistic predictions or conceal anomalies. Quantum simulations in laboratories attempt to mimic horizon effects using analog systems such as Bose-Einstein condensates, testing whether Hawking-like radiation can be reproduced. Each avenue of research tightens the frame around the paradox, but has yet to dissolve it. The cultural resonance of horizons has long been tied to the unknown. Ancient maps marked their edges with sea monsters, warning of uncharted waters. Mystical traditions described horizons as thresholds between visible and invisible worlds, places of passage where form dissolves. The black hole event horizon inherits this lineage, a frontier both physical and symbolic. Its role in the information paradox elevates it further, transforming it from a boundary of matter into a boundary of meaning, where the universe's capacity to remember or forget is put on trial. The inquiry continues without closure. Each proposed resolution generates new questions. Each experiment illuminates only fragments. Horizons retain their ambiguity, their dual status as both limits and sources. The tension persists between erasure and preservation, between the permanence of records and the fragility of memory, waiting for discoveries that may shift the balance but not dissolve the uncertainty. The singularity remains the most troubling feature of black hole physics. It is described as a point of infinite density, where space-time curvature diverges and known equations collapse into undefined values. General relativity predicts its inevitability under conditions of gravitational collapse, yet the concept of infinity within physical law signals not explanation but breakdown. To encounter the singularity is to confront the limits of knowledge itself, where predictive frameworks dissolve. In practical terms, the singularity cannot be observed directly. It is concealed behind the horizon, shielded from interaction. Its existence is inferred not through sight but through mathematics, emerging as a necessity within Einstein's field equations. Yet the same equations that describe planetary orbits and gravitational waves with extraordinary precision unravel when applied at this limit. The singularity is a point where the predictive continuity of physics ruptures, producing a conceptual fissure in the structure of science. Efforts to resolve this rupture have driven the search for a theory of quantum gravity, a framework that can integrate general relativity with quantum mechanics. Among the candidates are string theory, loop quantum gravity, and other approaches that replace the singular point with finite, though exotic, structures. Some propose that space-time at Planck scales is discrete rather than continuous, preventing infinite compression. Others envision that what appears as a singularity from outside is in fact a gateway to other regions of space-time, with wormholes or bounces replacing collapse. None of these models have yet been verified, but all seek to excise the infinity and restore calculability. The psychological resonance of singularities derives from their resistance to imagery. While horizons and tidal forces can be represented through analogy, the singularity offers no spatial metaphor. To imagine a point with no extension yet infinite density is to attempt visualization of the unvisualizable. Cognitive studies of the sublime suggest that when the mind encounters concepts beyond representation, it shifts from concrete imagery to affective response, awe, terror, or reverence. The singularity, in this sense, is less a picture than a feeling, a domain where thought ends in confrontation with its own incapacity. Cultural reflections of such boundaries are widespread. Religious traditions describe ineffable centers where language fails, the unnameable divine, the hidden source, the void beyond form. Philosophical systems, from Neoplatonism to Eastern mysticism, often describe ultimate reality as beyond predication. The singularity functions similarly in physics, not as an object of description but as a boundary condition where description collapses. Its presence in equations parallels these traditions of unspeakable centers, suggesting that the structure of thought encounters analogous limits across domains. Yet singularities also raise practical concerns for cosmology. If black holes contain them, and if the Big Bang itself emerged from a singularity, then the universe appears punctuated by points of breakdown. This challenges the assumption of seamless laws extending without exception. The universe, in this reading, is not wholly transparent to reason but riddled with sites of opacity. Such sites may conceal new orders of law, waiting to be discovered, or they may indicate that the drive to total explanation is itself misguided. Speculations extend further when considering what lies beyond the singularity. Some models propose that collapse may not terminate spacetime but transition it into new domains. The interior could connect to another universe, or to another region of our own through a wormhole structure. In these accounts, black holes are not only destroyers but bridges, their centers serving as conduits rather than terminations. Yet the mathematics of stability undermines many such visions. Wormholes may collapse too quickly for traversal, or quantum effects may prohibit their formation entirely. The ambiguity persists, unresolved between possibility and impossibility. Experimental physics has yet to touch these depths. No probe can cross a horizon and return data. No observation can penetrate the shield of lightlessness. What remains accessible are indirect signatures, the behavior of matter near horizons, the spectrum of gravitational waves from mergers, the shape of shadows captured by interferometric arrays. Each piece of evidence outlines the periphery, but the center remains concealed, a zone defined by inference rather than measurement. The tension between periphery and center mirrors patterns in human cognition. The unconscious, as described in psychoanalysis and neuroscience alike, is inferred from slips, dreams, and symptoms rather than observed directly. Its structure is reconstructed from effects, never grasped in itself. The singularity plays a similar role in physics, inferred from the distortions it produces at distance but inaccessible in itself. The parallel highlights not identity but structural similarity. Both domains contain cores that resist penetration, known only by their shadows. As technology advances, the periphery may be resolved with greater clarity, yet the center will likely remain untouched. The singularity is not simply hidden. It is defined as unreachable by the very laws that describe it. This paradox positions it as a permanent limit within science, a reminder that even as instruments expand horizons, there are boundaries that recede with every step forward. Speculation continues, with each theoretical advance reshaping the contours of the unknown without erasing it. Singularities remain as markers of unfinished inquiry, their presence a signal that the architecture of physics is still incomplete. They compel continued exploration not through revelation but through their refusal to yield, drawing investigation onward into questions that remain suspended between mathematics and imagination.